Hi, and welcome to this next in a series of videos on the 2D frame analysis module in the Structural Engineering Library. If you're just joining us, we're working on a braced frame, single bay braced frame, and we're up to the point now where we'll talk about defining and assigning loads to the model. We'll look at two different types of loads in the video here. One will be member loads and the other will be joint loads. So let's start with the member loads. I'll come to the Members and Loads tab and then move to the Member Loads subtab. And what I have in mind for member loads for our frame is to apply a uniformly distributed dead load and a uniformly distributed snow load on the beam in the model. So I remember that my beam is member B. We could also come back to the sketch to refresh on that if need be. So I'll select member B, and then what I'll point out is that we have two categories here to use to assign member loads. One is for point loads on the selected member, and the other is for the purpose of applying distributed loads to the selected member. I'll focus on the distributed loads category, and then what I'll do is click the Add Load button. That populates a line in this table that indicates that yes, the selected line will be considered active. That's a toggle that we can select or deselect as we see fit if we want to experiment with different sets of loads at the same time. The next column is the direction, and here I'll show that we have a variety of options for the direction in which a uniformly distributed load can be applied. It can be applied in the global X direction or the global Y direction. We also have the option to apply uniformly distributed loads in the projected X and Y direction, only meaningful for sloping members, particularly useful for snow loads on sloping members, where the codes and design standards typically tell us that the design snow load applies to the projected area of a sloping roof member. We have the option also to apply a uniformly distributed load in the member local X or local Y direction, and I would encourage you to take a look back at the video that discusses establishing boundary restraints and member end conditions for a refresher on the member local coordinate axis system. And then we have an item here which is a temperature load that can be used as well. So what we'll do is leave our option set to the global Y direction, and then the next thing that we need to do is specify the location of the starting and ending points of the load that we're about to define. Now the convention in the program is that if we leave the starting and ending locations set to 0, 0 in the uniformly distributed loads section, that will be interpreted as a full length load. So for convenience, we don't need to come in and set the ending location equal to the member length in order to ensure that a member distributed load runs full length. We can just do 0 and 0. Then we'll come over to the dead load category, and what I had in mind was a 0.2 kip per foot dead load. What we're doing here is indicating the magnitude of the applied load at the start of the member and at the end of the member. So we have the option, obviously, of defining linear varying loads if we need to. In this case, I'll set the starting and ending magnitude equal to 0.2, and I would just point out that our note reminds us that based on our decision back on the General tab, we chose the option to specify that positive magnitudes of loads that are applied in the global Y direction will be interpreted to act in the negative Y direction. In other words, positive loads are thought of as downward or gravity type loads. So for convenience, we don't need the negative signs in front of the dead load magnitudes. And then I also said that we would use a snow load on this model that would be 0.3 kips in my sketch that I have. So I'm going to enter a magnitude of 0.3 and 0.3 for the starting and ending magnitudes, and now we have fully defined the uniformly distributed loads on the beam member in our model. The next thing that I'd like to apply is a point load, in fact 2 point loads that will be applied to joints. So I'm going to move back to the Joints and Loads tab, and then I'm going to move to the Joint Loads and Results sub-tab. Here, what we can do is select the joint that we wish to load, and then work in the table over at the right-hand side to apply the concentrated load at the selected node. So what I'd like to do is I'd like to put a wind and a seismic load on the upper 2 nodes, which will be nodes 2 and 3. So back to the Joint Loads and Results sub-tab, I'll select joint number 2, and then I'll come over to the table and I'll use the Add button. Again, it inserts a line. It shows me that by default the added load will be considered active when I run the model. For the direction, what I'd like to do here is choose the global X direction. These will be lateral loads. And what I'd like to enter is a magnitude for the wind load of 7 kips. And I'd like to enter a magnitude for the seismic load of 9 kips. So now I've created a load that's been applied to joint number 2. And then I'd like to do the exact same thing for joint 3. So I'll choose joint 3 in the joint list at the left, click the Add button to create a line in the table, indicate that the load is to be applied in the global X direction, and then what I'll do is come over to wind and set that magnitude to 7 kips, and click in the seismic category and set that magnitude to 9 kips. I would note that when I enter a value, I always make it a habit to click in a different cell or a different field to register that value and make sure that that the value is stored in the program. So there's obviously a lot more that could be done in terms of applying loads to this model, but for the purposes of demonstrating how to apply the typical loads to a fairly simple brace frame, I think that this will suffice. The next step in the process will be for us to take a look at defining load combinations, and we'll tackle that in the next video. Thanks very much for your time and have a great day.